Welcome to For the Love of Wisdom, a YouTube channel on philosophy, free thought, and critical thinking. In this video, we're going to be looking at conditional proofs. This is part of a series of videos on symbolic logic, and this video is going to be assuming that you already know the material that I've covered in previous videos on symbolic logic. In particular, you should know about the rules of inference and the rules of replacement. If you have not seen the previous videos, you should be familiar with how these are presented in Irving Koppe's books. Otherwise, I recommend that you go back and watch the previous videos before you watch this one. Let's start with a description of what conditional proof is. Conditional proof is used to prove a conditional, which is an if-then statement, such as, if Hillary Clinton is president, then the president is a woman. And the way conditional proof works is like this. First, you have the conditional that you want to prove. Here we want to prove if P then Q. So we start by assuming the antecedent of the conditional. That's the first part of the conditional. So we assume P here. And we try to derive the consequent of the conditional, which is the second part. So we try to derive Q. And if we can derive Q from the assumption of P, it follows if P then Q. So we can conclude the conditional. So let's begin by looking at our first proof. We begin with a simple proof just to give you an idea of how conditional proof works. This proof has only one premise. The first premise is if P then Q. And what we want to prove is if P then Q or R. Now you'll see that what we want to prove is already in the form of a conditional. So we want to begin by assuming its antecedent, which is P. And we do that on line 2. We assume P. Notice we have a vertical bar to the left of P. That is a scope identifier. Each assumption that we make has to occur within a scope. And what we derive within the scope cannot be used outside of the scope. Now what we want to derive here is Q or R. How can we get Q or R? Well, with P we can get Q by modus ponens, and then we can use addition on Q to get Q or R. So that's how we'll proceed here. As you can see on line 3, we use modus ponens to get Q from lines 1 and 2, and then we get Q or R by addition from line 3, and that gives us our conclusion here, if P then Q or R, by conditional proof from lines 2 through 4. And notice that we can use what's within the scope of our assumption only with the conditional proof. We cannot take something within this scope and assume it or use it outside the scope. All we can do is say that all we can conclude here is a conditional of the form that takes the assumption as the antecedent and what's finally derived as the consequent. Here we have two premises. The first premise is if P then Q, and the second premise is if the disjunction Q or R, then the conjunction S and T. And we want to prove if P then S. So naturally the first thing we're going to do is assume that P is true. So on line 3 we have our first assumption, P, and we open a scope with that. And now how can we get S? Well, where does S appear? S appears in our second premise. We have S and T as the consequent of this conditional here. And how can we get S and T? Well, if we can get Q or R. And how can we get Q or R? If we have either Q or we have R, we can get that. Q is up here, and we can get that by modus ponens. So that's what we're going to do next. And on line 4, we get Q from lines 1 and 3 by modus ponens. And then we're going to get Q or R by addition. And that gives us the antecedent to this conditional here. Then we can use modus ponens on that conditional and get S and T. And now that we have S and T, we can just simplify and get S. And so we have derived S from P. We assumed P, and now we have S. That means we can close off this assumption and conclude by conditional proof that if P, then S from lines 3 through 7. Okay, let's now turn to an even more advanced, even more complicated uh, example of conditional proof. Here we have four premises. The first premise is if P then Q. The second is if R then S. The third is if T then U. And the fourth is P or the disjunction R or T. And what we want to prove is Q or the disjunction S or U. If you remember from the rules of inference, we have a rule called Constructive Dilemma, which looks very similar to what we're looking at here. Constructive Dilemma differs from this by having only two conditionals and a disjunction of only two terms. But here we have a disjunction of three terms and we have three conditionals. But it's basically the same kind of thing. For any number of conditionals you have, if you have the disjunction of all their antecedents, you can conclude the disjunction of all their consequents. And whether you just have one conditional or two conditionals or three or any number of conditionals, you can do that. But the rule of constructive dilemma applies only to the case where you have two conditionals and the disjunction of their antecedents. And we want to show that this, which we might call a constructive trilemma, is also valid, which it is. And we're going to use conditional proof to do that. Now notice that what we want to prove here is not itself a conditional. So how are we going to use conditional proof to prove a disjunction? Well, according to the rule of material implication, a disjunction is equivalent to a conditional. This disjunction here is equivalent to the conditional if not Q, then S or U. So what we're going to do is assume not Q and try to prove S or U. So on line 5, we assume not Q. And remember, what we want to get is S or U. Now notice S or U is also a disjunction. And that is equivalent to the conditional if not S, then U. So we can derive this as with a conditional proof as well by assuming not S. And so we do that on line 6. We make the assumption not S. And notice that when I did this, I added a second scope identifier here. We're now two scopes deep into this proof. Each new assumption creates a new scope that has to be nested inside any other scopes that already exist. And you cannot close a scope until you close the scope of any assumptions made within it. So we're going to have to close the scope of this assumption before we can close the scope of this outer assumption. Now we're looking to get U. Well, we can get U from 3 by modus ponens. But for that we need T. And T appears here in line 4. P or R or T. So we just need to get, if we can get not P and not R, we should be able to get T. We can get not P right away through modus tollens from lines 1 and 5. Then we're going to use not P to get R or T through disjunctive syllogism from line 8. And once we get not R, then we'll have T. Well, we can use modus tollens to get not R from lines 2 and 6. So now we have not R, and now we can get T. And we get T on line 10 through disjunctive syllogism from lines 8 and 9. And that allows us to get U through modus ponens from lines 3 and 10. This allows us to close this assumption and derive through conditional proof, if not S, then U. And remember, this is just equivalent to what we're going after, which is up here, S or U. So we have to do some transformations first. First, we're going to do material implication to get not S or U from this conditional here. And then we use double negation on line 13, and we get S or U, which is what we were going after. And now we can derive, if not Q, then S or U. We do that here on line 15, and then we can just have to do the same transformations that we did before to get our final conclusion. So we do a material implication on line 15 to get not Q or S or U, and we do double negation to get Q or S or U, which was the conclusion that we're trying to get. So that completes this proof. And the special thing about this proof here is that we learned how to do nested conditional proofs. Each time you make a new assumption, you have to nest its scope within the scope of any previous assumptions that you've made. And you have to close that scope before you can close any outer scopes. So you can nest as many assumptions as you'd like. You can have conditional proofs nested within conditional proofs, and so on, any number of times. It's perfectly valid. You just have to make sure that every line you derive is derived from within its scope. Well, it can be derived from an outer scope, but it can't be derived from a more narrow scope. So, say here I have T on line 10. I could not go to line 14 and derive T from here because this is a closed scope now, and I can't derive anything from within a closed scope. Let's now turn to a much simpler proof. Here we want to prove if P, then P or P. But notice one difference between this proof and the ones we've done so far. This proof has no premises. What we're going to try to do here is prove a theorem using conditional proof without the benefit of premises. So with a conditional proof, we can assume P, we can derive P or P, and then that will prove if P, then P or P. And we do that without the benefit of premises. So on our first line, we assume P. On the second line, we get P or P through the rule of addition from line 1. And now we are able to close off our proof and get what we were trying to prove. If P, then P or P from lines 1 through 2, conditional proof. So we've used conditional proof here to prove a theorem. And the benefit of being able to do this is, for one thing, we can use this to prove our rules of inference, or at least many of our rules of inference. And that's what we're going to do next. We're going to use conditional proof to prove one version of one of our rules of inference. Here we have a version of the rule known as tautology. It's saying that P is materially equivalent to the conjunction P and P. And we want to prove this. Well, notice this is not a conditional. How are we going to use conditional proof to prove this? Well, we're going to do that with the assistance of a rule called material equivalence. And this tells us that when two statements are materially equivalent to each other, that's the same as saying that if one is true, then the other is true, and if the other is true, then the first one is true. So this is saying that P is materially equivalent to Q is itself materially equivalent to the conjunction of if P then Q and if Q then P. So all we want to do to prove a statement of equivalence is to prove the two conditionals. Then we can conjoin them and use the rule of material equivalence to prove what we were going after. So that's what we're going to do here. First, we will assume P and try to derive P and P. And then after we get if P, then P and P, we're going to assume P and P and derive if P and P, then P. And we'll put those together and use material equivalence to get this. So on our first line, we assume P. On our second line, we get P and P from lines 1 and 1 through the rule of conjunction. We're just conjoining one with itself. And now we can conclude by conditional proof, if P, then P and P. And this is only the first part of what we need to prove what we are going after. Now we want to assume P and P. So we do that on line 4. We assume P and P. And then on 5, we get P by simplification from line 4. And now we close off that. And we get if P, then P, then P from lines 4 through 5, conditional proof. So we take the two conditionals we proved by conditional proof and we conjoin them on line 7. We get if P, then P and P, and if P and P, then P. And with that, we can conclude what we're going after, the material equivalence of P with P and P, from line 7 by the rule of material equivalence, which is shown here. For our last proof in this video, we're going to prove the other version of the rule of tautology. This says that P is materially equivalent to the disjunction P or P. We already did part of this in a previous proof. We assumed P and we used addition to get P or P, and we concluded through conditional proof, if P, then P or P. Now we're going to do the other part by first assuming P or P and trying to derive P. But bear in mind that we're not going to be using the rule of tautology here, because the rule of tautology is itself what we're trying to prove, and we don't want to use what we're trying to prove itself. That would be circular reasoning. So we're going to avoid using that rule right now. So on line 4, we assume P or P. Now on line 5, we do something unusual here. I'm assuming not P, but I'm going after P. Why would I assume not P when I want P? Well, what I have in mind here is that I'm going to create a conditional. With a disjunction, I'm able to deny. And when I deny the disjunction, I'll be using modus tollens to get a denial of the antecedent. And the antecedent of that conditional is not P, so I'm going to get a denial of not P. And that will be equivalent to P. So I'm going to use this conditional proof to get a conditional I can use to prove P with. That's what I'm going towards here. Now, just what consequent could I have which I could deny? Well, I have P or P here. If I have the denial of P or P, I could deny that. So I want to derive the denial of P or P. Now here's where we get into something that's a little tricky here. I have just derived P from lines 4 and 5 through disjunctive syllogism. Now notice that P is the opposite of what I have on line 5, which is not P. Between lines 5 and 6, I have a contradiction. Now I'm going to use this contradiction to prove what I want to get as the consequent for the conditional I'm going after. Because once I have a contradiction, I can use it to prove anything at all. The first step in proving anything at all from a contradiction is to use the rule of addition to add what I want to prove as a disjunct to one of the parts of the contradiction I have. So I have P here, and I just add not P or P to it. And since I also have not P, I can use disjunctive syllogism on this disjunction here and derive the denial of P or P. So I use this trick of taking a contradiction and deriving whatever I want. And so I derived not P or P from that. And now I can get if not P, then not P or P. And I do that here on line 9 through conditional proof from lines 5 through 8. And remember, the reason I want this is so that I can use modus tollens to get P. So first I take what I have on line 4, P or P, and I put it in a form that's going to work with modus tollens. I double negate it so I get not P or P. Then on line 11, I use modus tollens on lines 9 and 10 to get not P. Then I simply double negate that and I get P on line 12. And this now allows me to conclude through conditional proof if P or P, then P from lines 4 through 12. I assumed on line 4 P or P, and on line 12 I derived P, and that gives me my conditional proof here. Now that I've done a conditional proof going each way, I can conjoin them, and I get if P then P or P, and if P or P then P. And now that I have the conjunction of them, I can use the rule of material equivalence to get the conclusion I'm going after, which is this. P is materially equivalent to P or P. Now notice what I did in this proof here. Here I assumed the opposite of what I was trying to prove, and I derived a contradiction, and I used that contradiction to create a conditional I could use with modus tollens to get what I was actually going after. There's an easier way to do this known as indirect proof, where you assume the opposite of what you want to prove, then you derive a contradiction, and once you have a contradiction, you can say through the rule of indirect proof that your assumption was incorrect, and so you can derive its negation. And this is what we've done here is a more roundabout way of doing the same thing as indirect proof. And this is just to prime you to understand how indirect proof works and to give you an appreciation of having that rule in addition to conditional proof. And we'll get into indirect proof more in later videos. That concludes the proofs we're doing in this video, and now I have some homework for you to do. Here's 4 proofs I'd like you to complete, and I'll give you the solutions in a later video, so go ahead and try these out right now. Without using the rule of commutation, I want you to show that P and Q is equivalent to Q and P, because this is in fact one version of the rule of commutation, and I don't want you using that rule to prove itself. Now, without using transposition, I want you to prove that if P then Q is equivalent to if not Q then not P. Again, this is the rule of transposition, so I don't want you using it to prove itself. And here we have a version of the rule of association, so without using association, I want you to prove P and the disjunction Q or Q and R. Sorry, let me start over with that one. I want you to prove P and the conjunction Q and R is equivalent to the conjunction P and Q and R. And finally, one last proof, we have 2 premises here. The first is if P then Q, the second is if R then not Q. and I want you to prove the denial of the conjunction P and R. So thank you for watching. Go try these out, and look for a future video where I will be giving the solutions to these.